Our next speaker is Kirby Cook, a Science Officer, National Weather Service, Seattle. So you guys might be interested in hearing what he has to say or quizzing him as best you can on what he has produced for you over the years about the weather forecast for the Northwest coast. It's a challenging area, as you know, if you've sailed out here. And if you study a little bit, you find it's a challenging area. We use Cliff Nass's book on Pacific Northwest weather as sort of the poster child for coastal weather studies. So we're really pleased to have Kirby with us this afternoon.
Thanks, Frank.
Sure.
Thank you. So I'm going to cover a lot of stuff actually that Ken and Joe and Frank talked about. I'll touch on some of that as it relates to coastal weather and more specifically the Pacific Northwest weather. I'm going to try to go through that pretty quickly so there's time at the end for questions. So just in terms of what I'm going to talk about, coastal marine hazards, a little wind and wave 101, which we've already had a lot of, so maybe it's not so 101. Fog 101, weather patterns, forecast process challenges, and then some resources. And that's where hopefully I'll have some time. I'll go over our webpage and some of the things that you guys should have access to if you don't know already. So I wanted to start by framing the hazards in the coastal waters and the offshore waters. Strong winds, waves, steep or high seas, thunderstorms and water spouts. We do get them here in the Northwest. Hurricanes we don't get here in the Northwest or really in the West Coast for a lot of reasons, but that's certainly one of the more significant coastal and offshore hazards in the marine areas. Hazardous bar conditions, and then non-meteorological. A lot of people don't think of that, but there are more and more hazards that are related not to weather, but things like oil spills, vessel groundings, and we do support for those sorts of events. So the things that I'm going to talk about that are really specific to the area waters here are going to be these things. Strong winds, waves, thunderstorms, water spouts, low visibility, fog, that's a big one around here, and then hazardous bar conditions. So a little more on wind, and I know that we've heard a lot about this in more depth this morning, but wind is a function of pressure, which in itself is a function of temperature differences, and elevation. At sea level, though, it's really, we're talking about differences in temperature driving differences in pressure, and that drives wind. So in terms of weather systems, that's really what we're looking for. Differences in temperature, frontal boundaries, and differences in pressure. So low pressure systems, extratropical cyclones. Those are the things that we look at because they drive wind, and wind drives everything. So extratropical cyclones, fronts, land, water, thermal circulation. So in the Northwest especially, but on the West Coast, we have topography, terrain that affects marine weather. And that sounds kind of weird, but we have mountains that drive marine weather. And if you head up into the Alaska waters, it's especially true there. But at least in terms of how we approach the forecast, and I think Joe even mentioned this, it always starts with wind. This is where the forecasters start when they're working on the forecast. It's with wind. So wave 101, there are 4 basic types of waves in the world's oceans. Wind-generated waves, wind waves, swell, tides, seiches, and tsunamis. I'm going to talk basically about wind-generated waves. I'm not going to talk about tides or seiches or tsunamis. We've already had some of that. Excuse me. So this is where I'm going to skip over this pretty quickly, but waves form when wind energy is added to the water surface over a period of time. This is at a capillary sort of level and higher. But there are a couple things that are important. The main parts of the wave are height, length, and period. Wave growth, wave height is a function of wind speed. and duration, as well as the distance over which the wind is interacting with the water surface, and that's fetch, and we've heard about that this morning already. But for the forecast in our area waters, all of those things are really important. So it's, again, wind. We start with wind. The duration that the wind's acting on the water surface, and then the fetch. When we get into area waters over our interior waters here, we're very fetch limited. So that is a factor that affects, how big the waves can be generated over, say, Puget Sound, or how the Strait of Juan de Fuca, or even smaller bodies of water like Hood Canal. Waves grow and they move outside the forcing area and propagate until they break on a distant shore. And I think I've got some animations here. Maybe it's on this slide. Wave speed is a function of its period. And this is why swell can move faster than storm systems that generate that. And so we get waves, swell, that come from great distances away. They move pretty quickly. This is a nomogram, and this is one way you can, forecasters will use to connect the relationship between wind speed, duration, and, fetch. It's a simple sort of four-dimensional chart that forecasters use, and it's complicated, and it gets more complicated when you start looking at the spectrum of waves that we might be forecasting for. So, but let's see, I think I've got I've loaded these things up with animations, and let me step ahead and talk about the distinction between wind waves and swell. In our coastal waters forecast, we make that distinction. So we'll forecast a wind wave and a swell, except for in certain situations where it's very complicated, and then we will forecast a combined sea. So wind waves are locally generated waves. So they're basically seas generated in the immediate vicinity of an observer or a location, and it's forced by the local wind. They tend to be steeper and peaked at the top, and they break again when we see that period ratio of 1 to 7. Swell is a wind wave that's formed some distance away and has traveled over long distances. They tend to be longer period. They're rounded at top. They can be quite large, but because they have longer period, they tend to have less impact depending on the situation. This is the simplified wave speed relationship that basically shows that wave speed is a function of its period. It's 3 times the period. In deep water, that you can use that approximation in deep water. And then combined sea is basically a representation of, thank you.
Water.
Combined sea is a representation of that spectrum that Frank was talking about. It's not just a single, thank you, it's a sloped podium. It's not just a single wave. It's a whole bunch it's a spectrum of waves. And in certain situations, it's really hard to represent that spectrum. And so we will try to do that using a combined sea. In terms of impacts associated with waves, it's not just a function of how high the wave is. It's the steepness of the wave. And it's something that our forecasters are really cognizant of. And it has a lot to do with the various forecast products that we put out, like a small craft advisory. And these kind of distinctions, even on the bar, we look at wave steepness. And again, longer period waves are more energetic than short period waves, but they can have less of an impact, certainly on various watercraft. Longer period waves do have an impact, and it tends to be more on coastal areas. This is a part of our marine program, but not necessarily directly related to the coastal waters forecast. But we do have impacts along the beaches of Washington that are associated with longer period swell. If you're familiar with the area, this is Ocean Shores. There's some buildings out there that are built pretty close to the beach, and they have pretty defined criteria for the direction and period for swell coming in that they're very vulnerable to. And so we provide direct support to that community. When we see that in the forecast, we actually put out a specialized forecast just for them. We give them a call, and they can actually, they've had to evacuate some of these locations in certain situations. It's a little hard to see, but it's a thin spit of land, and what they worry about is the waves breaking through that spit and then getting into Grays Harbor on the backside. So the other significant impact or component to the marine forecast here in the Pacific Northwest that is impactful is fog. And there are some subtle differences, or maybe not so subtle differences, between kind of East Coast fog or fog in other areas and fog on the West Coast. So there are three types of dynamically forced fog. Advection fog or stratus, and that arises when you have advection of warm, moist air over cold surfaces. And that doesn't happen in marine areas on the West Coast very much. If you think about it, when do we have warm, moist air advecting over our waters? Almost never, right? The flow in the Pacific Northwest is coming off the Pacific Ocean. So it may be moist air, but it's not generally warm. When we do get warm air advecting over area waters, it tends to be hot, dry air in easterly flow, offshore flow situations. That's not going to cause fog. So advection fog typically happens on the East Coast, that pattern. Here on the West Coast, we have West Coast fog or stratus, which is a much more subtle situation and has a lot to do with, another animation here, has a lot to do with changes in the boundary layer. The boundary layer is the lowest part of the atmosphere where most of the weather happens. It's certainly where we work and live. It has to do with the moisture properties in the boundary layer, and that boundary layer growing or expanding, changes in the boundary layer depth, the moisture profile in the boundary layer, and the temperature profile, which drives saturation, and we get fog. So it's complicated. It's hard to forecast. It's a challenge. And you have situations where it's interacting with bodies of water. Here in Western Washington, we've got a lot of water that's very fine scale, small details, not very big, and it can be quite a challenge. The other type of fog that we see quite often is steam fog or sea smoke, and that's a situation when you have water temperature that's warmer than air that's moving over it. The image on the top there is the view from the forecast office here in Seattle looking out onto Lake Washington. We get a lot of this kind of fog in really cold situations where we get cold air that moves in from the north during the wintertime over Lake Washington, which is warmer, and we get fog that forms. That's a wintertime thing here and a little more rare than sort of the West Coast fog stratus situation. So fog's an important thing here in the Northwest and actually all along the West Coast. If you look at climatology for fog, in coastal areas, the foggy spots are the Pacific Northwest and the northeastern United States. So climatologically, we get over 40, I think that's 40 days a year on average of fog.
When you walk, stay close to the podium.
There is a seasonal signal to this. Here in the Northwest, our least foggy season is spring, and that really has to do with the seasonal cycle. We're getting a little more sun, we have a little more instability, so it's a little harder to see fog develop. We still see fog, but the foggiest season is actually in the fall along the coast of western Washington, Oregon. There's a secondary peak down in Oregon along the Northern California coast. So there's a seasonal cycle, just like everything else, to fog, but it's complex here in the Northwest, a little different than other areas. I wanted to talk a little bit about coastal weather patterns that are common that we watch for. And the first one is our extratropical cyclones, low pressure systems, deep low pressure systems. These are the systems that are responsible for our strongest winds. not just in the marine areas, but over land and in general in the Pacific Northwest. So this is, if you're from this area, you're probably well aware of the Columbus Day storm from 1962. This is the strongest storm in the Northwest, windstorm in the Northwest. We often can see with these storm systems, well, not often, but we can see Category 3 hurricane winds, and as well as the matching low pressures associated with the central pressure of these storms and sustained winds. So this storm, I think, had a max gust of 110 knots and I think 92 knot sustained winds. So a hugely damaging storm. They're responsible for the strongest winds that we see. That obviously affects the marine areas just as much as it does the land areas. And they can be massive storm systems. So these storm systems can affect areas from Northern California all the way up to Alaska. This is a plot of groupings of the most common storm tracks for these storm systems. And I wanted to show this because we tend to talk about these in terms of the impact to the land areas, the public areas in the Pacific Northwest. But you'll notice that the storm track for all of these storms go first through the marine area. So this is an offshore. The way they've organized the structure or the track for these, climatology for these storms, this is the classic path. And again, you can see they track all the way up along the Oregon and Washington coasts. Inside of 130 West, this is an Oregon track, a Washington track, and then a Vancouver Island track. But, so if I sort of step through those, you know, the impacts to the marine area are pretty significant. If you go back to the plots that Joe showed of where boats are going in and out of our coastal waters, these storm systems obviously affect those areas. So extratropical cyclones, low pressure systems, they can be a significant driving mechanism in terms of strong winds in our area, and subsequent seas. Winds drive the seas, not just locally. And they're challenging because the track of the low is significant. So small changes in the track of the low affect drastically things like the distribution in the wind field and the impacts associated with the wind field, as well as the waves generated from that. This is just a loop that I grabbed the other day. So this is, the white lines are mean sea level pressure from the GFS model, and you can see the wind barbs. That's a representation of the wind forecast from the GFS, and the color-filled contours are significant wave height from the WaveWatch 3 model. So it's two models overlaying just a simple relationship, and this is real time. This is for, I think, Sunday. So this is the forecast that was valid for this coming Sunday tomorrow. And I just wanted to highlight that, you know, you can see here an extratropical, gotta find the button. So you can see, if you watch down here, you can see this extratropical system develop and spin up pretty quickly as it moves up into the Aleutians. You do see it, the wind field that develop as a function of that, and the seas that are generated as a function of that strong wind field. And obviously they're gonna affect the coastal areas of Alaska and the Aleutians. But early on, you'll see the system kicks off some winds that actually move out ahead of this, or not winds, but waves and winds that move out ahead of that. And those effectively will move into the Pacific Northwest as well. So these storm systems produce obviously local winds, but they also produce marine impacts that travel great distances across the North Pacific. The other coastal weather pattern that produces actually most of our winds, so this is the most frequent cause for strong winds in the marine area, are frontal boundaries. And the classic kind of pattern where we have, usually they're cold fronts, they can also be occluded fronts. Occluded fronts here are, actually can produce some of the strongest winds that we see. But these are the most common, a cold front. And the pattern is for areas along the coast, North-south oriented bodies of water like Puget Sound, Hood Canal, we get the strongest winds ahead of the front, and they're southerly winds. And once the front moves through and we get the northwesterlies, west and northwesterlies behind the front, places like the Strait of Juan de Fuca, the eastern Strait of Juan de Fuca, the northern inland waters, they get the strongest winds with the westerlies behind the front. So it's a complicated pattern, but quite often this is what produces more of the strong winds that affect our coastal areas than anything else. And this is just a model loop of the front that came through yesterday, actually, and it's a little tough to see. It looked better when I recorded it on our workstation. But if you watch this for a second, you'll see the frontal boundary will move in with southerlies ahead of the front and then west to northwesterlies behind it. And this was just yesterday. So we get these all the time, and they are really the forcing mechanism behind most of the strong winds and marine impacts in our area and the West Coast in general. So this is where I want to start to talk about terrain or mountain-influenced weather impacts, marine impacts. And the first of which is gap flow. Gap flow is a big forcing mechanism for a lot of the marine weather that we experience in the Northwest. The Strait of Juan de Fuca is a gap, and it behaves like a canyon in a lot of ways, and it drives typically on any given day the strongest winds in our marine area are in the Strait of Juan de Fuca. The Strait of Juan de Fuca is honestly probably why our marine program is the most active program that we have. We probably have some sort of a watch or a warning advisory product out every other day because of the Strait of Juan de Fuca, and that's all driven by gap flow, which in turn is driven by simple pressure patterns. So this is a situation where you've got a gap in terrain, a canyon, or the Strait of Juan de Fuca, and you've got high pressure on the east side of that and lower pressure on the west side, and that's going to set up a situation where you're forcing air through that gap. And there's some compression associated with that, and so in this situation you can have stronger winds in the exit region of that gap, and we see that all the time in the Strait of Juan de Fuca. When we have easterly flow in the Strait of Juan de Fuca, the strongest winds are going to be in the west entrance, right off of Nia Bay and Buoy 87 out there. The other side of that is when we have strong onshore flow, the strongest winds are in the central to eastern strait. This also describes a unique wintertime situation here where we get Fraser River outflow from the Fraser River Canyon up in British Columbia, where we get offshore flow, we get strong northeasterly winds coming out of the Fraser River, and that'll work its way down through Bellingham into the northern inland waters, and we can get very gale strength winds up there in an area that doesn't necessarily see a lot of gale winds, and it's out of an odd direction. It's offshore. It's coming from the land. And so those situations can be very, very impactful, and they tend to be cold in the wintertime, so we can actually see freezing spray and very, very cold temperatures. So those are two examples of locally driven gap flow. There's actually two types of gaps, so you can get a sloping gap, and that would be where something like the Fraser River, where you've got a gap in mountainous terrain, or a level gap, which would be like the Strait of Juan de Fuca. This is a scatterama or plot of offshore flow and showing that situation of easterly flow through the strait, offshore flow where we get the strongest winds right off the northeast tip of the Olympic Peninsula. And this is about the only time we can see gale strength winds driven by a simple pressure gradient difference like this in the western entrance of the Strait of Juan de Fuca. It's usually, the more common case is onshore flow, and so we get the strongest winds in the central and eastern strait. So when the flow pattern is reversed, the strongest winds are here in the exit region. The other really common area where we hear about gap flow in the Northwest is the Columbia River Gorge. And I don't think we see too many situations where the flow affects the marine area there, but it certainly does in the Portland area and along the river itself. Very significant flow. The other weather pattern that's significant terrain influenced marine weather is coastal jet. And this is a pattern driven by low-level baroclinic structure that results in winds that often exceed 35 knots, so gale strength winds, and obviously potentially significant marine impacts. It's caused by pressure differences, temperature differences between the water and the land, coupled with coastal terrain, coastal mountain ranges. It's very common along the Washington, Oregon, and California coastline, typically in the summertime. So does anybody know what a sea breeze is? What drives a sea breeze? So a sea breeze is where you've got differential heating between the land and the water. Land heats up more than the water, generating a breeze that moves onshore from the water. What happens if you've got a mountain range and you have that pattern where it's warmer over the land, cooler over the water, but you've got a mountain range right on the coast? You don't get that onshore breeze. So it forces the breeze to curve to the right in the northern hemisphere down the coast. And that's what drives low-level jet. Often we'll have a capping inversion that helps enhance that low-level jet along the coast. It can be very persistent. It's diurnally driven. That means it happens every day with the sun. The diurnal heating during the day drives this circulation. And so it's persistent, it occurs every day, and it can have impacts that occur every day, especially in the summertime. The other coastal weather pattern that occurs and affects the marine areas in the Pacific Northwest, certainly everywhere, but surprisingly here is convection, thunderstorms, and waterspouts. And actually in western Washington, our convective hotbed is actually the coastal waters of Washington. So we see thunderstorms over the coast all the time, and then when the system moves onshore, the convection dies out. So one of the areas that we see frequent thunderstorm development, especially in the shoulder season between the wintertime and spring, this time of year, is the coastal waters. In fact, the frontal boundary that moved onshore yesterday, everyone was expecting to see some convection with that. We didn't see a lot of lightning with it, but it's a very common pattern. We see waterspouts quite often with this pattern. So what we're looking for is three things for thunderstorms. Moisture. So obviously over the coastal waters we have a lot of that. Lift and instability. Instability, hot air rises, and so when you have a situation where you have an unstable air mass, if you have any mechanism to nudge that, any lifting mechanism like a frontal boundary, that's enough to kick off that instability, and you're going to get thunderstorm development. Those are the three ingredients that we look for, and this is very common this time of year where we've got potentially cool air over a moist coastal boundary layer and a frontal system like yesterday moving into the area, and we can get thunderstorms or waterspouts. This is a waterspout up in, I think this is Bellingham Bay, western Whatcom County. Very, very common. The other hazardous condition that's common not just in the Pacific Northwest, but it's certainly something that we deal with, are hazardous bar conditions. And this is driven by oceanography and meteorology. So the shoaling effects associated with the bar are often enhanced by ebbing tidal currents, as well as offshore winds and surface currents. And so these are the things that we watch for. We do a bar forecast for Grays Harbor Bar, a specific bar, a worded bar forecast, not just a graphical forecast. And Portland is, they also do a bar forecast for the Columbia River Bar. I think those are the only two worded bar forecasts that are produced, at least on the West Coast. Humboldt Bay, they do a bar forecast, but it's modeled, it's graphical, and I'll show you some examples of what that looks like. This produces a lot of impact. This is, I think this is the picture of the Coast Guard boat, that's the Columbia Bar. But you can see that the kinds of seas that can arise very quickly, and it's simply a function of ongoing onshore swell coupled with an ebbing tidal current, and especially if we have offshore winds. So this one I might have to. So this is an example of the Nearshore wave prediction model Joe mentioned earlier over the Grace Harbor Bar. So this is using the SWAN model. It's a very high resolution model. It resolves the bathymetry with the bar. That went fast. So it's able to resolve see if I can play that again. It's able to resolve not just the harbor entrance itself, but the bathymetry underneath the entrance to the harbor. They have to go out and survey that bar every few years. It moves around. But it also takes the WaveWatch 3 input, our wind forecast, and generates this high resolution forecast. It actually runs out 5 days. We only do a bar forecast 24 hours. So this is one of the things that we look at. It gives us high resolution data where we really don't have anything else to hang our hat on, and it's a complicated process. This is available online, by the way, and I'll show you this in just a second. So these are all of the things I'm talking about are available online. So they're available for you guys to look at. There we go. So I wanted to talk a little bit about the challenges the forecasters face in terms of the marine forecast and forecasting in general here in the Northwest. Terrain is a plus and a minus. It complicates everything. It's a plus in that it doesn't move. So we can count on, it's always going to rain more over the mountains. The Olympic Mountains don't move. So that helps provide some predictability to flow through the Strait of Juan de Fuca. It's complicated because it messes up the very simple models that we have in terms of how the atmosphere works. So when you have a frontal boundary coming in, looks really neat and nice over the ocean. The second it moves on shore, it falls apart and changes because of things like friction and other physics. So it's a plus and a minus, but terrain complicates everything. And there aren't a lot of places in the world where you have to deal with terrain when you're doing a marine forecast. Highly variable fetch. So over the coastal waters, we have different fetch that's at play than we do over the interior waters. It's a real issue over our interior waters. Hood Canal can either have a really long fetch, depending on the flow, or a very narrow fetch, right? If there is a westerly component to the wind at all in Hood Canal, it's a very narrow fetch. Hood Canal is very, very narrow. But if you get the right wind direction, blowing right up Hood Canal, the canal is like, I think 80 miles long. That's a pretty big fetch. So we have to deal with those kind of things, and it's very, very challenging. We have limited observations. I think I have a plot. We have very limited observations, especially at the surface. And so this is a huge challenge in terms of our marine forecast. We often don't really know what's going on. So we'll issue products based on model forecasts without any kind of observational support. We have satellite data, we have ASCAT winds, and we only get those twice a day, and if we're lucky, it's at the right time. If not, we have to rely on the surface observations. And out over the coastal waters, we have one buoy in our coastal zones, and we have one island, a destruction island, and that's it. And often they don't make it through the winter, so we'll get a storm and buoy 41 goes out, and that's it sometimes until the next fall. Do you have a question?
Did you just get a radar installation on the peninsula?
We do have a radar. We have 2 radar, and that's also very useful. But it's limited. It's not going to see everything. The radar, it tilts up. So the further you get from the radar, the higher the sample area is, and so it's not going to see everything. But it's definitely useful. It allows us to track fronts as they come on shore. Yeah.
I know there's a test going on with the sail drone boats.
Yep.
But I haven't heard how they're working out.
That's expanding, and I think there's a pitch to do that more, and that's very promising. We've looked at it over the season, and any data is useful. So.
They are producing useful data.
Oh yeah. If they're in the right place, they're not always in the right place, but yeah. Uncertainty. So that was the other thing I wanted to talk about is the role of uncertainty, and this has come up a couple times. I was actually really pleased. I think somebody showed. I think it was Ken or was it Frank? You showed Ed Lorenz this morning. Somebody showed Ed Lorenz this morning, and I had a slide with Ed Lorenz. He's the one that showed the sensitivity in the atmosphere to initial conditions, the uncertainty in the atmosphere. And it's really the limit on the predictability of the atmosphere and the ocean. And if you think about how we are able to forecast, our primary tool for forecasting anything beyond about 6 hours is a computer model. And all that computer model is a mathematical or a numeric representation of our understanding for how the atmosphere works. And that's flawed. We don't understand how things work perfectly. Okay, so our math is flawed. It's limited. The other part of this, though, is to run that model, you have to know what's happening now in the atmosphere or in the ocean. So you have to start that model on good initial conditions. And that's where the limit on the predictability of the atmosphere and the ocean is we cannot perfectly observe what's happening now, let alone produce a model that's going to forecast it perfectly. So Ed Lorenz showed that. He showed the sensitivity to small perturbations in those initial conditions and what that does to the forecast. So the atmosphere is inherently unstable. It's inherently unpredictable. There's variability in terms of the certainty of what's going to happen in the atmosphere. So how do you deal with that? I think several people showed this already. What you can do is you can run a model over and over and over again using slightly different initial conditions to represent, hopefully, the actual uncertainty that's in the atmosphere relative to the current conditions. And so this is a plot of what that might look like with a simple, we call these spaghetti plots or a plume plot. Each one of these is the same model run over and over and over again using slightly different initial conditions. And you get a sense for maybe where the forecast is more confident, where it's less confident, right? Where all the forecasts are pretty close down here, and then they expand as you get further out in time. The idea would be this is where there's less confidence in the forecast. There are a lot of ways that you can use this. You can use this by just eyeballing it like this. Where do I think there's a lot of uncertainty? You can use it to generate probabilities. So we can do things like what's the probability of wind speed exceeding 21 knots in a particular area based on running a model over and over and over again. The challenge that our agency faces is we're pretty much a deterministic organization. So we give you one forecast. And so how do you take an ensemble approach and apply it to, I have to give you one forecast? And it's sort of like picking the right horse. And so I think what we try to do is we look at those ensemble forecasts and pick the one that's most likely, and that's the one that we represent. But if you do things like read our area forecast discussions or any kind of forecast discussion, you'll see the forecasters talking about the underlying uncertainty in the forecast. That's where this is coming from. Okay. I wanted to talk about another kind of challenge that's specific to the marine program, and I think Joe talked about this a little bit, and it distinguishes, it shows up in our marine program especially when you compare it to the rest of our forecast responsibility. And this will make maybe a little more sense as I work my way through this. So this is our analytics, the statistics from our Twitter account. So we do a lot of social media here in the Seattle forecast office. This is for last year. So this is for February 1st to February 14th of last year. Who's from Seattle? Does anybody remember what happened February 1st to February 14th of last year? The Snowmageddon, right? Okay. So, and you can see that. This is just for that 2-week period. These are our stats just on Twitter. Okay, so we had 21.8 million impressions. We had 21,000 retweets. So we have all these metrics linked to this, and one reason is it's easy. We can track this stuff, and we use this to track our forecast. You know, when are we busy? What's our busiest weather? And we do this all the time. If you were to walk to the forecast office right now and ask what's our biggest weather, and in fact, if you were to ask everyone in this room, you just validated it. It's snow, right? It's a 4-letter word here. Snow is a 4-letter word. Why is that? Why is snow such a huge thing here and other things aren't? But it doesn't really kill people. Our biggest fatality thing, if you want to look, you can track impact in a lot of ways. If you look at fatalities, it's heat. Heat is the most dangerous weather phenomenon here. If you look at damage financially, it's flooding. Snow, it comes up because it does affect everyone, but it's not as deadly or dangerous. Another way we can look at this is, and I'm going to stop after this, I'm almost out of time, but is web traffic. So this is our web traffic starting October 1st, running through last week. So this is this year, this isn't last year, and the blue lines are just our overall web traffic. You can see our total page views. Anybody want to venture a guess as to what those spikes are? Snow, it's snow again, right? And so we had several record-setting flood events. Where are they at in there? You know, they're back in here. And if you look at staffing, so another way we can look at how important weather type is based on staffing, and our big staffing is flooding. So when we have flooding, we staff our office up a lot. So there are a lot of ways that you can look at traffic, and I just wanted to point this one out because this little red spike right here, when I put this together, I started to look at this and what is that red spike? And if you dig, if you come in, the way the system works is it tracks what page is being viewed, but it's this ndbc.noaa.gov data forecast marine. And there's also a marine link in here that shows up below. So that, if you look at it this way, that was our 3rd most busiest day, and it was marine. So marine is hugely important to our area, and it depends on how you look at it. But one of our challenges is we don't see that. When it snows, the first thing that happens is our phone starts ringing, and we know something's going on. But for the marine forecast, we don't get that. So we'll put a forecast out, we don't have observations, and we don't hear from people very often, so quite often we don't know what's going on. And it's one of the biggest challenges with our marine program is there's sort of a disconnect. And it's one of those things that we're continuing to work on, and it's obviously important. So I've got other stuff, but I've talked way over my time. Yeah.
Not over yet.
What's going on? So, you know, one of the things that we've been pushing, this is what happens, by the way, when it snows. This is the forecast office. That's everybody goes to the window and starts looking at. That's right. We have windows. You know, Twitter. So you can send us information on Twitter. If you've got a cell phone and you're on your boat, send us a tweet. All you got to do is throw in hashtag WAWeather, WAWX, and we'll see it. And if you've got location services set up on your Twitter account, we'll know where you're at. And even better, if you put a picture in there, it goes back to those stats that we use heavily. So let us know. Give us a call. We have a marine forecast desk that's staffed 24/7, 365 days a year, and it's one person, and that's all they're doing is marine. And we've got a phone line. Give us a call.
Thank you very much.